Hi everyone, welcome to Chemistry class by Shravani. So, as usual, we are going to study and continue the carboxylic acids and derivative as part 4. So, this part 4 video class, we are going to study a new topic. Before that, let's just have a recap of whatever we had learned in the previous class. Okay, so in the previous class, we have seen the preparation methods for the preparation of carboxylic acids, and within that we have specifically seen the general method of preparation for aromatic and aliphatic, which includes the hydrolysis of acid derivatives. As we have seen, the acid derivatives include nitriles, amides and esters. Okay, nitriles have the functional group and they are also called as cyanides. They have the functional group of CN, cyano, and amides CONH2, and esters COO functional group. So all these functional groups are basically called as acid derivatives, and hence therefore the hydrolysis of these acid derivatives will give us the carboxylic acid, whether it could be an aromatic carboxylic acid or it could be an aliphatic carboxylic acid. That's why it is the most general method. Of course, there are many other methods for the preparation of aromatic and aliphatic, but as per our syllabus we are seeing the specially hydrolysis of acid derivatives. Okay, and here you can see the link for which you can have the access to the previous class where I have explained the preparation through the general methods for the hydrolysis of acid derivatives. If you click the hyperlink here, you will definitely go to the class where you can have a detailed explanation for this preparation with lots of examples and mechanisms. Okay, now let's have a quick look for the hydrolysis of acid derivatives with the reactions. So when you go for nitriles, as I said, they are also called as cyanides, and the functional group is represented as RCN. And remember, R can be aliphatic or aromatic. What is aliphatic? It is an open chain structure, and aromatic, which is a benzene-like ring structure. So you can prepare either aliphatic carboxylic acids or aromatic carboxylic acids through this hydrolysis of acid derivatives method. So if you observe here, the RCN, that is a cyano group, when consumes 2 moles of water molecule in presence of acid, which is acting as a catalyst here. So these 2 moles of water molecules are consumed by the cyano group and will result in the formation of RCOOH. You can observe the number of carbons R is remaining same, and the C of cyano group is converting into COOH. That means the number of carbons are same and they are retained in this process. There is no loss of carbons or gain of carbons in this process. And this acid acts as a catalyst so that it boosts or it fastens the hydrolysis process to this acid derivatives cyano. Next, for amides, we have this process. So, amides can be hydrolyzed to carboxylic acids either in presence of acid or in presence of base. Acid is represented with H+, and you can have the supply of acid from mineral acids such as HCl or H2SO4, whatever it may be. But remember, it should be in a dilute case. Anyway, when we are taking water in addition with this acid, it becomes dilute. And base, it can be taken from sodium hydroxide, which is NaOH, or KOH, which is potassium hydroxide, and this boosts up the addition of water molecule to this functional group. So, unlike cyanides, amides take just one water molecule for this hydrolysis process, where the amides are converted into carboxylic acids. I hope you remember that the cyanides take one water molecule and form the intermediates of amides, and which then take another water molecule and finally give carboxylic acids. But the only thing is that in presence of acid, amides give a perfect carboxylic acid, whereas in presence of a base, they give a salt, which is a carboxylate ion. This is carboxylic acid. You can see the hydrogen attached to the OH of COOH, whereas when you run the reaction in presence of base, the proton of OH is lost. Therefore, it forms an anion which is called as carboxylate ion in this case. Okay. And similarly, esters also. Esters can also be hydrolyzed to give carboxylic acids in presence of acid as well as base. So, this is the formula for esters, which is RCOO R prime. Here I have given R prime so as to indicate that this can be a different alkyl group also or same alkyl group also. So, even if you take the similar alkyl groups or same alkyl groups, it doesn't matter, or different alkyl groups also, it doesn't matter. Not only alkyl, you can take aryl and alkyl, whatever it may be. That's why we have taken this method for the general method of preparation for aromatic as well as aliphatic carboxylic acids. You can see that here esters also similar to amides, they take one mole of water molecule in presence of acid or base and result in the formation of carboxylic acid or the salt of carboxylic acid. So when you have this salt of carboxylic acid, in order to convert into the carboxylic acid, you just need to add this a simple dilute solution, or you have to run up the reaction with a dilute acid so that this carboxylate ion O- will add up with H plus from the acid and result in the formation of COOH. So here if you observe here, the esters when catalyzed with acid to form RCOOH, which is a carboxylic acid, this is a reversible reaction. Okay, so this is a reversible reaction, whereas this is not a reversible reaction. This is called an esterification and this is called as saponification. We will learn this in the later part where we are going to read the chemical properties of carboxylic acids. So anyway, we have a detailed explanation of all these things in the previous class where you have been given with the hyperlink in the previous slide. So yeah, I hope you have cleared the exercise of the previous class. We have three questions based on the previous class where I have given this is a functional group of ester and what happens to ester when it is reacted with water molecule in presence of acid. We have seen that esters on reaction with water in presence of acid, they give acids, carboxylic acid, the corresponding carboxylic acid. So if you see the the ester and just cut this and in presence of OCH3 we will get OH. That means a propanoic acid. Similarly, benzonitrile, it will give you sodium benzoate since it is taking base catalysis and it will consume 2 moles of hydrolysis. And here I have given a cyanide group, but I have given only one water molecule and I have asked you what is the reagent that is required to convert acetonitrile to stop at the amide stage. So we know that when nitriles consume water, they will result in the formation of carboxylic acid, as you can see here in the previous example. But I want you to know how it can be stopped at the intermediate stage where amide is formed. So at this stage, what we have to do is we have to take a very dilute acid and pour excess of water so that it doesn't go for further reaction, or even you can cool down the temperature so that the reaction is freezed, so it doesn't process forward. So this is the quick recap of previous class. Now let us enter into the main content of today's class. So what are the contents? Let us see. So as a part of today's class, we are going to see the general methods of preparation, which include for aromatic as well as acid aliphatic. So there are two methods. One is hydrolysis of acid derivatives and the other one is using grignard reagent. We have seen this hydrolysis of acid derivatives in the previous class. Now we are going to focus on the method of preparation for generally as aromatic as well as aliphatic using grignard reagent. And what is the next content that we are going to see? Along with this, we are going to focus on the special methods. Special methods, when I say, it is for aromatic, not the general. General means for aliphatic as well as aromatic. The second one we are going to focus is what are the methods that are used for specially preparing aromatic carboxylic acid. And though there are many methods, we will focus as per our syllabus from arenes. Okay, so these are the two topics that we are going to focus today. So let's have a look at this. So first is grignard reagent. What is grignard reagent? As you are very well known from your intermediate days, grignard reagent is a methyl magnesium halide, alkyl magnesium halide or aryl magnesium halide, whatever it may be, and it is represented with RMgX, where R can be aliphatic or aromatic and Mg represents the magnesium, X is a halogen, and this halogen can be bromide, chloride and iodide. Very less often fluoride is taken due to its very reactive properties. Therefore, it is often bromide and chloride are frequently used when we take the grignard reagent. And as you know, this grignard reagent has the structure RNGX, where magnesium is an electropositive atom. So, due to its high electropositivity, it will take up a partial positive charge, so that the R, which is a hydrocarbon one part, will get a partial negative charge. Therefore, the R can be a anion type or nucleophilic type molecule in this grignard reagent. That is the speciality of this grignard reagent. Hence, it is used for many reactions where R is acted on the other group as a nucleophile. So therefore, here the R of grignard reagent undergoes nucleophilic addition with CO2, which is a carbon dioxide, or for the reaction purpose we have to take in the solid form of carbon dioxide. What is solid form of carbon dioxide? It is dry ice. It is dry ice. You have seen in, I hope you have seen in movies where we will be seeing like a smoke and everything is coming instantaneously, and it is nothing but dry ice. When you observe or when you watch movies, you can observe such a scene where the smoke will be coming from dry ice, which is a solid CO2. And so, as you know, CO2, C is bonded with two oxygen molecules through a double bond, and it is a linear molecule. Due to the bonding of highly electronegative oxygens with carbon, therefore the carbon will have a partial positive charge. Therefore, there is a chance that the R from which is having a partial negative charge will act on the partial positive charge having carbon of carbon dioxide. And for this process, for the experimental purpose, we have to use dry ether, because RNGX grignard reagent is highly reactive and is very versatile reactant. That's why in order to keep the reaction under pace, we have to use dry ether as a solvent. And in this reaction, when grignard reagent reacts with carbon dioxide in presence of dry ether, there will be a salt formation, and this salt upon acid catalyzed hydrolysis gives carboxylic acid. That means it is a two-step reaction. First, grignard reagent reacts with carbon dioxide, and then we will get a carboxylic acid upon hydrolysis of the resultant salt form. So, this is a two-step one. And as I said, the R can be alkyl or aryl group. This is very useful for the preparation of wide range of carboxylic acid because R can be alkyl or aryl. So we can have a wide chances of having this grignard reagent. And as you very well know that grignard reagent can be easily prepared by reacting alkyl halide with magnesium. So therefore, we can have many types of alkyl halides which are widely available, easily available. Therefore, can be easily converted into grignard reagent. Therefore, it can be used for the preparation of carboxylic acid. But the only fact that it is not used, it cannot be used for the formation of formic acid. Why it cannot be used? Because there is no corresponding R for this. Because methanoic acid or formic acid, the formula is, I hope you remember, it is HCOOH. That means H should act as R here. So we cannot have a hydrogen magnesium halide which cannot be called as a grignard reagent. Therefore, this is the only flaw for this process. And except this, we have the wide range of choices where you can choose this process for the preparation of carboxylic acid. And the beauty of this reaction is that you will get N carbon to N plus 1 carbon. What is this N carbon to N plus 1 carbon? The resultant carboxylic acid will have 1 carbon excess than the taken R of grignard reagent. As we have seen in the previous examples where we have taken the hydrolysis of acid derivatives, we have seen that the number of carbons doesn't change because we are just probing hydrolysis. We are removing other functional group, but whatever the R chain is there, it will remain as it is. That means the number of carbons are remaining same when we are using the preparation method using hydrolysis of acid derivatives. But this preparation methods is used for preparation of higher homologous acid carboxylic acids. So it is a atom gain. I can say N carbon to N plus 1 carbon. So you can prepare a higher carboxylic acid from a lower grignard reagent. So let us see the mechanism involved and the reactions for this. So this is the theory behind the addition of preparation of carboxylic acids using grignard reagent. So if you look at the reaction, this will be the thing. I said the grignard reagent will add to carbon dioxide in presence of dry ether and it will form a salt, which upon hydrolysis in presence of acid will give the required carboxylic acid, of course a side product. So, as I said, carbon dioxide has a linear structure where carbon is having two oxygens through a pi bond to it. Therefore, being highly electronegative, these oxygens gain the electrons of this carbon and carbon will get a partial positive charge. And due to this high electropositivity of magnesium, it will have a positive charge and it will have a partial negative charge. And as we know, this negative charge will be attracted by the positive and positive will be attracted by negative. Therefore, one can easily expect that R minus will go and add on carbon of carbon dioxide and this magnesium part will go and add on oxygen of whatever the thing. As soon as R comes and adds upon carbon, these pi electrons will be completely shifted to the oxygen, giving a complete negative charge to oxygen, probing or prompting the magnesium to get add to this. Therefore, we will have the structure like this. So, R will come and attack on carbon, R is added to carbon and whatever the pi bond, it is shifted to oxygen. So, the pi bond is disappeared here. So, O will become O minus and this MgX will become this Mg plus. Okay. So, this way, since when we have this minus and plus charges within a compound that is called a salt, so this salt has to be converted into corresponding carboxylic acid. In order to get rid of this MgBr, which is a cation, we just need to brush up this reaction with acid catalyzed water. So therefore, the proton from the acid will come and attack on this O minus forming OH. Okay. So this is the steps behind this. So the nucleophilic carbon in the grignard reagent adds to the electrophilic carbon in the polar carbonyl groups. So electrons from the CO move to electronegative oxygen, creating an intermediate magnesium carboxylate complex. So in the step 2, this was regarding the step 1. So in the step 2, this is just a simple acid-base reaction. So the protonation of carboxylate oxygen creates the carboxylic acid product from the intermediate complex. You can have a clear and simple look at the mechanism here. So whenever the alkyl R group is represented in blue and MgBr it is represented in green and CO2 is in black, so that you can have which part is coming from which reagent in the final product. So CH3 from this grignard reagent is getting added to carbon, and as soon as it gets added to carbon, the pi bond will shift on the carbon. So it will form a negative charge here. So CH3 will bond it to carbon. So the blue part, you can see CH3 is bonded to carbon and pi bond is shifted to oxygen, therefore O minus, and MgBr will be having a plus charge. So OMgBr. So this one upon addition with acid proton, so O minus will be added to H plus, so that this will be the one. So if you observe this whole reaction, CO2 in the carboxylic acid, you can easily see that CO2, this CH3COOH or RCOOH I can say. So within COOH, H is from this hydrolysis, COO from this carbon dioxide, and this R is from Grignard reagent. So if you want to prepare any carboxylic acid of your choice, you can just compare this with, we just need to write the structure of the carboxylic acid and then compare the R with the structure, so that you can identify which Grignard reagent you have to choose for that. So now let us see more examples. Okay, so here you can see that this is Grignard reagent and this is carboxylic acid. So if you see the final structure RCOOH and initial RMGX, what is retained? Only R from RMGX is taken. R from RMGX is taken, and COOH comes from this CO2 and hydrolysis water. So whenever you want to choose the Grignard reagent, first write down the structure of carboxylic acid which you have to prepare. If I want to prepare acetic acid, which is CH3COOH, so my R Grignard reagent should contain CH3. So this will be CH3MgBr. Okay, so this is called as methyl magnesium bromide. This is methyl group and magnesium bromide, and we know this is acetic acid. So methyl magnesium bromide upon reaction with carbon dioxide in presence of dry ether and followed by the hydrolysis in presence of acid will give you the acetic acid. As I said, this is a general method for the preparation of aromatic as well as aliphatic. Just now we have seen the aliphatic, now we will see the aromatic also, but from a little previous step also. Actually, this was our required one. So I have deliberately given you a previous step for the preparation of phenyl magnesium bromide, that is RMGX. As I said, this Grignard reagents can be easily prepared from alkyl halides, corresponding alkyl halides, by just reacting the alkyl halides with magnesium in presence of dry ether. So in order to have benzoic acid, so my structure of benzoic acid is benzene attached to the COOH group. So when you prepare carboxylic acid from Grignard reagent, this COOH comes from CO2 and this proton of hydrolysis. So my R will be this benzene ring. R will be benzene ring. So RMGX, that means benzene ring MgBr. So in order to have this phenyl magnesium bromide, I just need to react this phenyl bromide with magnesium. So bromobenzene it can be also called. So this is the reaction. So convert this bromobenzene to corresponding Grignard reagent, which upon hydrolysis before the reaction with carbon dioxide, it will give you benzoic acid. So this way you can prepare n number of carboxylic acids where you can have the easier preparation from Grignard reagent. So here is a mechanism for easier remembering. So R minus from the Grignard reagent will add upon the carbon of carbon dioxide, and this as soon as it adds up, the pi bond from the CO will be transferred to oxygen giving O minus. So therefore my structure will be RC double bond O minus. So this upon hydrolysis with water will give you RCOOH. Okay, so this is the mechanism. Now, so this way you can have preparation method from carboxylic acid, where it is different from the hydrolysis of acid derivatives in one way that acid derivatives you can have only n carbon to n carbon, whereas this grignard reagent gives you n carbon to n plus 1 carbon. Now let us move to the second topic of today's content. What is that? That is special methods for the preparation of aromatic carboxylic acid. Till now we have seen the general methods which include the preparation of aromatic as well as aliphatic. That means using hydrolysis as well as using grignard reagent you can prepare aromatic as well as aliphatic. But now today we are going to see specially for aromatic carboxylic acid. So in our syllabus, though there are many types of methods to prepare aromatic carboxylic acid, we are focusing on special methods which include the oxidation of alkyl benzenes, which are also called as arenes. Okay, when you have a side chain on the benzene ring, so they are called as arenes. So the oxidation of side chains upon the benzene ring or oxidation of side chain of arene using the oxidizing agent such as potassium permanganate KMnO4 or potassium dichromate K2Cr2O7 or any other oxidizing agent, maybe concentrated HNO3 or whatever it may be. So there are many types of oxidizing agents which we will learn later. So the most famous are KMnO4, but here KMnO4 acts as a good oxidizing agent in presence of a base which is an alkali. I call it as, therefore I write it as alkaline KMnO4. That means KMnO4, it should be added with some base or KOH, whatever it may be. And whereas K2Cr2O7 is a acidified one. So in presence of acid it acts as a oxidizing agent, and KMnO4 it acts as a oxidizing agent, of course even in presence of acid, but a strong oxidizing agent in presence of a base. So for this purpose, for this reaction we will take alkaline KMnO4 as a main example, whereas you can also use acidified dichromic acid for further also. So here if you see the example, so here it is a benzene ring which has a alkyl attached side chain which is a CH3. So somebody can name it as methyl benzene, or the most common name is toluene. Okay, so toluene upon reaction with alkaline KMnO4, and when it is probed for heating, just you need to give small little heating, so it will oxidize the carbon attached to the ring to COO, carboxylate, corresponding carboxylate. So COO minus. Anyway, the potassium ion from this KMnO4 will compensate the negative charge so that a salt is formed, and this will give you potassium benzoate. And this, as we know, in order to convert a salt into corresponding carboxylic acid, we just need to do hydrolysis in presence of acid. Okay. For this case, we don't need base because we are in lack of proton. So that's why we have to supply proton. So this hydrolysis cannot be performed in presence of base. In order to have this salt formation converted into corresponding acid, we should have an acid supply. Okay. So therefore, acid catalyzed hydrolysis will give you this salt into carboxylic acid. So what happens in this reaction? These oxidizing agents will oxidize the carbon attached to the ring. The carbon attached to the ring, not the extra carbon which is elongated. Whatever the first carbon attached to the ring will be oxidized to the corresponding carboxylic acid. So if you observe here, we have only one carbon attached to the ring. But here we have a little longer chain where two carbons are involved. This is ethyl benzene. This is methyl benzene. So, however long may be the chain, only the first carbon attached to the ring will get oxidized. So, if you even have a structure like this where you have n number, whatever it may be, it will just oxidize this first carbon, that's it. So, this is not bothered. So, however the long chain, the carboxylic acid will be only formed at the first carbon. So I hope you are clear with this. So however the long chain may be, only the first carbon which is attached to the benzene will be oxidized and converted into COOH. But for how long? So it converts the first carbon attached to the benzene ring to corresponding carboxylic acid, but the only condition is that it should have at least one hydrogen attached to this carbon. That means you may have any number of branches or whatever it may be the elongation, but the carbon attached to the ring should have at least one hydrogen. At least one hydrogen. Then only this reaction occurs, because KMnO4 takes up this hydrogen to process this to COOH. So what happens if there is no hydrogen? We have further branching in this. So earlier this was cumene example. Now we have a tertiary butyl benzene. Now we have a carbon where there are no hydrogens attached to the carbon which is attached to the ring. So this is the first carbon attached to the ring. It should get oxidized, but it is in lack of hydrogens. Therefore, it will not undergo reaction with alkaline KMnO4. Therefore, no oxidation occurs, no reaction is observed. This is a very tough one. So, in this way, you can use carboxylic acid, alkaline KMnO4 for the oxidation of arenes. So, this is the special method for preparation of carboxylic acid using arenes. But there are other methods also, though these are not in your syllabus. I am just giving you for your knowledge. So, yeah, before going to that, let us see some more points of this oxidation of arenes to carboxylic acid. What if there are more number of carbons attached to the ring? We have seen that even the side chain, whatever may be the long, only the first carbon will be oxidized, and that too the first carbon will be oxidized only in the case it has at least one benzylic hydrogen. That means the first carbon attached to the ring should have at least one hydrogen. So only in that case the oxidation occurs. What if there are more number of groups attached to this ring? So if you observe here, there are two groups attached to this benzene ring. So one is CH3, other one is CH3. What happens if this molecule, which is metaxylene, you can observe the position of these groups are meta. If it is side by adjacent, ortho, next meta. If it is opposite, then it is para. So this is called xylene. If they are side by side, then it is orthoxylene. If they are opposite, then it is called paraxylene. So earlier, when there was no extra CH3, only CH3 was there, we called it as toluene. Okay. So we can also say it as orthomethyl toluene, but a common name is metaxylene. Okay. So here you can see that there are two groups attached to the benzene ring. So however may be the number of groups attached to the benzene ring, if it is attached to the benzene ring, then that carbon, if it has a benzylic hydrogen, definitely it will get converted into corresponding carboxylic acid through oxidation by alkaline KMnO4 followed by hydrolysis. Okay. So however may be the number of carbons attached to the benzene ring, if the carbon attached to the benzene ring consists of at least one hydrogen, then such group will be oxidized to COOH. So metaxylene will form isophthalic acid. Okay. So metaxylene will form isophthalic acid. This is the beauty of this. So you can form a dicarboxylic acid also using this special method, which is oxidation of arenes. Yeah, even if you have three groups attached to the ring, then also you can oxidize. All the three groups will be oxidized to the COOH groups. Okay. Now, this is a more pretty example where you can enjoy the effect of this one. So here, if you have benzene ring which is infused with a cycle or cyclic ketone, and it has a extra functional group NO2. So regardless of the other functional groups, if the benzene is attached to a carbon, whether it is in the fused ring or whatever it may be, if the benzene ring is attached to carbon which has hydrogen, then it has to convert into COOH. Therefore, this will be broken and this C will be converted to COOH. Similarly, this C will be converted to COOH irrespective of the presence of nitro group here. So this is an example where you can have this HNO3 also as an oxidizing agent. So, however, the structure may be, if the benzene consists of a carbon bond which has a hydrogen to it, therefore it will be converted to COOH in presence of oxidizing agents. So this was for our syllabus, and for your extra knowledge, these are the other methods for preparation of carboxylic acids from aromatic compounds. So you can use other aromatic alcohols and hydrolysis of aromatic acid derivatives, also oxidation of aromatic carbonyl compounds. As we have seen, this aromatic acid derivatives upon hydrolysis will give you aromatic carboxylic acids, and the oxidation of aromatic alcohols. So what are aromatic alcohols? The alcohol group is attached to this benzene ring. Okay, so in this purpose you can use either alkaline KMnO4 or K2Cr2O7 or HNO3, whatever it may be, for oxidation. So all these will give you this corresponding COOH group. And as we have seen previously, hydrolysis of aromatic acid derivatives. So here I have taken the example of cyano. This cyano upon hydrolysis will give you COOH. So just mark CN with COOH. Similarly, this is an ester COO, and this COO bond will be broken to form a COOH upon hydrolysis. So this way you can have more number of methods for the preparation of aromatic carboxylic acids from other functional groups such as alcohols, acid derivatives and carbonyl compounds. But in our syllabus we had specially the oxidation of arenes. So in that we have to remember specially the properties such as the carbon attached to the ring only will be oxidized, and then the carbon, though it is attached to the ring, if it has the hydrogen, benzylic hydrogen only, it undergoes oxidation, and however maybe the number of carbons attached to the ring, all will be undergoing oxidation. So this was the main these were the main points under the oxidation of arenes. So as a part of today's class, we will have an exercise. Try to solve this. Okay, so give the preparation of phenyl acetic acid using Grignard reagent. Okay, so we have seen the method of preparation of carboxylic acids using Grignard reagent. So just refer to that page and you can just try out this question. A hint is that first write down the structure of phenyl acetic acid and compare the R group required with the general reaction where we had for Grignard reagents. So you will get an easy answer. And can you just write the products for the following? So for this purpose, maybe you have to Google. The thing is, deliberately I have given an extra chain. In the example, I have given only one carbon OH, but here I have given CH2CH2COOH. So phenyl ethanol. So what happens? I have given you in the previous slide that if you have just CH2OH, only one carbon and OH, whether it is alkaline KMnO4 acidified dichromate, both will give you benzoic acid. But what if you have CH2CH2, two carbons, okay, two carbons with alkaline KMnO4, what happens and what happens with acidified dichromate? So are both give the same product or both differ in product formation? So you can just think of it. The hint is that alkaline KMnO4 is a strong oxidizing agent than acidified K2Cr2O7. Okay, so this is the hint. You can just Google it. Otherwise, anyway, we will see the solutions in the next class. And the last question for this is CH2 ethyl benzene. So ethyl benzene, this is an arene. We have already taken this example in this part also. You can just refer back. What happens to this ethyl benzene if you oxidize with alkaline KMnO4 and followed by acid hydrolysis? So I hope you will definitely try out this, and otherwise we will just see those in the next class. So this will be the end of our class. So therefore we will go for the conclusions. So in the conclusions, in today's class, what we have seen the general method of preparation of carboxylic acid from Grignard reagents. Okay, so in the previous class we have seen the general method of preparation of carboxylic acid using hydrolysis of acid derivatives. But in today's class we have seen a new method for the general preparation of carboxylic acid, which can be used for the preparation of aromatic as well as aliphatic carboxylic acids. Okay, so that is using Grignard reagent. The formula for Grignard reagent is represented as RMgX. R can be aliphatic group or aromatic group, and X is a halogen. And then followed by that, we have seen a special method for the preparation of carboxylic acid, which is the oxidation of arenes. Okay, so oxidation of arenes will give you carboxylic acid. And apart from this, we have also seen some other additional reactions for the preparation of aromatic carboxylic acid. Of course, they are not in your syllabus under the degree for Osmania University. Those are other functional groups of aromatic compounds such as alcohols, acid derivatives, and carbonyl compounds, which upon oxidation also they will give corresponding carboxylic acids. Okay, so this is the topics that we have covered. So in the next class, we definitely have some more new topics. And until then, thank you for listening. I hope you will definitely solve the exercise, and I hope you have enjoyed the class and understood it very well. And definitely do comments, give your comments so that I can improve myself. If you really like the video, kindly do share and subscribe the channel, and don't forget to post the comments. It will definitely give an encourage to me to correct my mistakes as well as to improve myself. Your cooperation is very required for me and is also a boost for me. Thanks a lot for listening to me. Have a nice day. Definitely we'll meet in the next class. Thank you and have a nice day. Bye.